Okay, it's 12 o'clock Wednesday. It's time for the Iowa Learning Farms webinar. We made it to July of 2026. Happy to be here today. I'm Matt Helmers with Iowa State University and the director of the Iowa Nutrient Research Center. And I'm really excited for our webinar today. We have with us Dr. Chad Penn. Dr. Penn is a research soil scientist with the USDA Agricultural Research Service in West Lafayette, Indiana. He is also an adjunct professor of soil chemistry at Purdue University. He's been doing some great work, one of the world leaders on phosphorus removal structures. And so he's going to talk to us today about removing dissolved phosphorus and nitrate with phosphorus removal structures using steel turnings in a bottom-up flow configuration. With that, Dr. Penn, the virtual floor is all yours. I guess just one comment. If you have questions, please type those in the chat box and we'll get those to Dr. Penn at the end of his talk. Okay, now the virtual floor is all yours, Chad.
All right, perfect. Thank you. All right. We thank Dr. Helmers for giving me this opportunity to speak to all of you. I did speak very broadly on phosphorus removal structures to you. I don't know if it's been 2 years, maybe it might be 3 years by now, but that was kind of a broad introduction to what they are and how they work. So now I'm going to get a little bit more specific into basically a case of how one of these structures performed. Designed a certain way with certain media. There's lots of different structures we built, but this is one that we thought would be interesting to those of you in the Midwest. So the focus of the P removal structures, just a quick review. It's dissolved phosphorus. So dissolved phosphorus is the target of P removal structures. And the reason why is because it's a more potent eutrophication agent than particulate phosphorus, which is phosphorus bound onto sediment. The reason why it's more potent is because aquatic organisms can immediately uptake dissolved P from the water. That's not true for particulate P. The bioavailability of particulate P depends on the conditions of the water body. Some sediment, it may release that phosphorus, maybe not, depends on pH, mineralogy, degree of P saturation. Some sediment, in fact, can absorb dissolved P when it reaches the water body. So we're focused on dissolved P. So sediment loss is, as far as particulate P goes, the main way that we control particulate phosphorus losses is through basically any practice that prevents erosion. And in most cases, the majority of your phosphorus is lost as particulate P through erosion. And we can stop that again. Like, we have lots of best management practices for preventing erosion and capturing sediment, and that's great. But sometimes when we get in a situation where we have soils that are built up very high in phosphorus, even preventing erosion will not stop the loss of dissolved phosphorus. So in that case, we need a new best management practice, a new tool that's specifically for getting at dissolved P in soils that are built up very high in phosphorus. We call those legacy P soils. So again, the target for P removal structures is dissolved P, specifically from legacy P soils. And in this case, I mean by that soils that have at least 100 milligrams per kilogram of maleic 3 phosphorus. Although I am seeing some people adapt this to make this worthwhile on sites that are not necessarily legacy P soils. But for example, our friends in Wisconsin, especially in Brown County, Jeremy Freud, the county engineer there, is building these, moving them around just in the springtime to capture the spring flow from CAFO sites that aren't necessarily built up high in phosphorus, but they get a lot of flow from recently applied manure. But usually it's for legacy P soils. The reason why is because legacy P soils, they're called legacy P for a reason. It's because when you build up a soil very high in soil test phosphorus, it tends to stay high for a very long time, even after you cease all phosphorus applications. This is an example of some data from Eastern Shore of Maryland. Varies from soil to soil, but the trends generally look the same. What they found from their study where they artificially built up soils to several different levels of soil test P, almost to 600 milligrams per kilogram in some cases, in one case rather. And then they began the process of drawdown with no more P additions, corn, wheat, beans rotation. And they found that to decrease soil test P from initially from when it's between 300 and 400 milligrams per kilogram, to drop it down to safe levels again can take between 20 and 30 years. So the problem is during that time period of drawdown, which you have to do to get to the root of the problem, bring that soil test P level down, eliminate the source. Every time you get a flow event, you're losing some dissolved P. And during that period, that's why we developed the phosphorus removal structure to work in conjunction with nutrient drawdown, where you basically have a large landscape scale size filter to intercept that water before it reaches a water body. And that material is bound. That material has a high affinity for phosphorus. Three necessary components for a P removal structure. They're very diverse in appearance. They can be applied to a variety of situations, and we've got plenty of examples on that over the years. But at the heart of it, you need an effective PSM filter media, phosphorus sorption material, in sufficient quantity, enough quantity to handle the load for the site and to be able to handle the peak flow rates for the site. You need to design it such that they can handle the peak flow rates at a sufficient contact time to remove the phosphorus. And you need to be able to retain and replace those filter media, those PSMs, when necessary.
Chad, real
Sir.
quick, can you, down toward the bottom of your screen, there's a little pop-up there. If you can hit
Oh,
hide so we can see
there we go.
your pictures better. So thank you.
Okay, sorry about that. There we go. So you follow those three main component requirements for P removal structure, and you can apply them to a lot of different situations. And we've done that. We've built them to treat runoff for overland flow in boxes. We've built them directly in ditches, tile drains. That's the form I'll talk to you about today, a specific example one at least, and also even blind inlets. We have built a blind inlet to treat surface water containing PSMs. We call that a modified blind inlet when we put filter media in it. We have one just outside of Ames that was constructed by the graduate student Adam Bussman, and then with doctors Amy Kalita and Dr. Supir. This is a cost shared practice. It was 782. Now it's a national standard at 624. So it's in the equip. For filter media, there's a lot of different filter media that can be used. A lot of them are industrial byproducts. Some of them work better than others. Metal filings is one of my favorites, most cost effective. That's what we'll be talking about today. There's also manufactured media. We've tested a lot of these different both byproducts and manufactured media. Manufactured media tend to be very efficient per unit mass, but they're generally very expensive, usually so expensive that we don't even bother putting them in the field, with one exception, activated alumina. Okay. In this case that I'm presenting today, and since you're in the Midwest, the most obvious place to apply P removal structures is to treat tile drains. And basically we bury a bed of filter media to intercept the tile drainage water. It can be contained in a tank, or it can just be a buried bed, depending on the material and the size of it. And these can be configured to flow from the top downward through the media, or to flow from the bottom up. And in this case, we're going to present a bottom-up flow. Now, sometimes the only option is to be able to use a bottom-up for several reasons. Sometimes, just due to a lack of hydraulic head, the tiles generally, they all outlet to ditches. Some sites will require a bottom-up flow regime. Maybe the outlet is located miles away from where you want to install it. You have to make it flow from the bottom up. Or maybe there's not enough head at that ditch to make it flow from the top down. But regardless, a bottom-up flow regime through the filter media is going to result in constant water saturation conditions, which can potentially lead to anaerobic conditions. which could be a problem for iron-based filter media due to re-release of previously absorbed phosphorus that was bound onto the iron. So in the past, mostly I've generally only done iron-rich media to flow from the top down to prevent that from happening, but we've been studying the possibility of going with bottom up for iron-rich media. So a previous lab research showed that anaerobic conditions generally do not occur very readily in those filter media when they're saturated with water. And if you did get anaerobic conditions, it generally did not release very much P. So at the lab scale and also the pilot scale, it looked pretty good. But before I give the green light, I want to do some testing in a field structure in a real bottom-up flow unit in the field with iron-based filter media, and that's what I'm presenting here. Basically, just that we want to evaluate a phosphorus removal structure with bottom-up flow using iron-based PSMs, specifically steel turnings. So the site, it's a 4-hectare field located in the St. Joseph watershed. It's a 6-inch tile main that we've been monitoring intensively for 20 years now. And there was, previous to this P removal structure, there was a different P removal structure at the site that we removed when we built this one. The site at the time of construction in July 2021 had soil test P of 125 milligrams per kilogram, Mehlich 3, producing a flow-weighted mean concentration over 0.2 milligrams per liter dissolved P. Perfect site for testing this. And in general, it produces around 5.6 million gallons of water per year. Peak flow, I'll get to that. The drainage outlet for this site, however, is located very far away from miles away from the field. So we had to use a bottom upward design configuration. So we wanted to build a structure. This was both a demonstration and research structure. So there's some things that we did that we wouldn't normally do, but I'll get to that. But the goal was to be able to remove around 40% of the year one load and handle at least 120 gallons per minute of flow with no bypass of untreated water, right? If the water doesn't flow through the media, it doesn't get treated. It can't just flow across the top. It has to flow through it. It's a filter. So we want to treat all the water. So for the design, we used a septic tank to contain the media. Normally, for this type of media, the metal shavings, I don't use tanks. Usually I build very large buried beds, keep the cost down, and then you can make it really big. Usually I only use septic tanks for when we're making filters that have your more potent and expensive per unit mass manufactured filter media like the activated alumina. And we have several of those that we've done. I can provide information on about that. But in this case, we put it in a tank just because it's for research and for demonstration. We wanted to be able to take people out to the field, pull the manhole cover off the tank and show people. You can't do that when it's a buried bed in the ground. It's just, you're just walking on the ground. There's nothing to see at all. So this tank is a fixed size, obviously, 4.1 by 1.7 meters. And so for the design then, normally we use the P-trap software, use the design function. There's a design function and an evaluate function on that software. Normally use design for designing a structure, but in this case, because it was a fixed area, I kind of use it slightly unorthodox, but I use the evaluate bed function in order to determine what the ideal filter media thickness is for achieving our flow rate goals, our retention time goals, and our P removal goals. And those goals were, again, 120 gallons per minute, and we wanted to have at least a 3-minute contact time, retention time, and remove 40% of the year one load using the 8% steel shavings mixed with pea gravel. So I iteratively changed the PSM thickness under that evaluate function until all the constraints were met. Again, it was a bit of an unorthodox use, but that's because we're using a fixed area tank. So the contact time goal or retention time goal is 3 minutes. And those of you who heard me talk about using steel shavings before, you might know that I always say use 10 minutes for a contact time for steel shavings because you get more removal. So why am I not using 10 minutes in this case? And the short answer is because we're using a tank. Because we're using a tank, we're limited in the PSM volume. This tank is relatively small for metal shavings. It would be fine for a more potent manufactured filter media, but for metal shavings, we generally want a much bigger bed. So because it's a limited area, we have a trade-off between being able to handle a really high flow rate and the pee removal ability, right? So we could pass the water through faster and get 100% of the flow to go through it. But if we do that, our removal efficiency isn't going to be quite as good. On the other hand, we could have a much slower flow rate, longer contact time, 10 minutes, not be able to handle all the flow, all the peak flow, but have a higher removal efficiency for what goes through it. So there's a balance there, right? And so I had to make that choice. I went with designing it for 3-minute retention time goal at peak flow rate. Again, you really want to be able to hit the peak flow rate, handle the peak flow rate for these things, because that's when the majority of your dissolved pee is being transported. This really captures how important contact time, what an impact contact time has on pee removal for this media, at least. For other media, it's not as sensitive to contact time. But here's your phosphorus removal curve with loading for a 3-minute contact time versus a 10-minute. So it makes a huge difference for this media. Again, other media, it doesn't matter as much. So we went with the 3-minute one for this design, so we could handle 100% of the flow and not bypass anything. This is the P-Trap software, the inputs and the output. So in order to achieve that goal, it would take what turned out we would need 9 tons of the PS of that filter media, the iron shavings mixed with gravel, approximately 30 inches deep, and 3-minute contact time. Predicts that in the year one, if it flowed at peak flow, 120 gallons per minute all the time, at that 3-minute contact time, at least 3 minutes, around 3.6, you'd get only 25% removal. But if it was a 10-minute contact time, you'd get more closer to 71%. Okay. In reality, the flow in the field is going to vary. You're going to have peak flow, and then you're going to have much low flow. So it's going to be a combination of the two and everything in between. So the goal was to imagine if these were put together, both of it overall, we'd get 40% removed. This is a schematic and some pictures of the structure itself. Again, we normally wouldn't put metal shavings, gravel in a tank, but this was for research and demonstration. So here's the inflow tile, water coming in. We use a flow control structure to serve as a bypass in case the filter got clogged or couldn't handle the flow, where that water could crash over the boards and continue going on. But as such, in the normal circumstances, with the stop logs in there, it forces the water down to the structure, flowing downward into the media where it flows from the bottom upward and back out, treated water out. We're monitoring flow rate and concentrations of both inflow and outflow. We have aeration pipe that we did not use in case we got clogged up with sediment. We could aerate it. That was never a problem, so we never even used it. The metal shavings, we like these because they're very cheap, $300 a ton. You mix 8%. You mix 8% with the gravel. They rust. Iron oxide has a strong affinity for phosphorus. When you're done, when it's all over, you end up mostly with red rocks, red gravel. Okay, we get right to the results. What did we see for phosphorus leaving the site before being filtered? Overall, the flow weighted mean concentration was 0.33 milligrams per liter over 4 years. This failed to mention this was over 4 years. Over that 4 years, delivered 16.5 kilograms of dissolved pee, 3.75 kilograms per hectare, almost 1 kilogram per hectare per year. 50% of the discharge occurred in year 1 of the 4 years. And 83% of the discharge of 4 years came from storm flow. That 83% of discharge carried 96% of the dissolved pee load. Base flow was 17%, which is a good chunk of the flow, but that 17% discharge only carried 4% of the dissolved pee load. Again, reiterating the point, you want to treat dissolved phosphorus, you want to handle the high flow rates, the peak flow rates. That's when a lot of it's going to get moved. And there was a decent amount of sediment coming through there, even though it's a tile. Nitrate, or nitrogen rather. There was negligible ammonium, so I'm going to show the nitrate only. Flow weighted mean concentration of nitrate over 4 years was 6 milligrams per liter. And the concentrations for nitrate was generally much more consistent and less flashy than dissolved P. Dissolved P the concentrations tend to follow the flow rates, not as much for nitrate. 278 kilograms of nitrate nitrogen transported and left that site in over 4 years. 77% lost in year 1 and year 3 combined. Those are the years that had the most discharge, by the way, but the losses were not correlated to flow rate. How did we do in dissolved P removal? Well, in year 1, of the total load year 1, we removed 38% of everything that flowed into it year 1. Over the 4 years, it removed 22% of everything that went into it. So in year 1, it was 2.6 kilograms, which is pretty good for for such a small structure that had iron shavings in it. We could have put a more potent filter media in it and probably gotten more, but again, for this media, we wanted to test, bottom-up flow for this particular media. That was pretty good for such a small unit. Normally, we put this particular media in very large beds of many, many, many tons. In practice, however, at this removal, we would have had the filter media replaced after year 1. But again, this was for research, so I let it go for 4 years. We wanted to see what would happen. We were close to our goal of 40% for the year 1 removal. But here's the removal plotted with our peer removal curves, ideal peer removal curves, the 10-minute curve removal and the 3-minute curve, 3.5-minute curve. And the blue dots are what we actually measured in the field. And so what we have is something in between because, well, in reality, in the field, our contact time was in between. So we had you have highly variable flow rate in the field. So when it's running peak flow, that's when it's going to be running about the 3.5-minute contact time. And other times it's going to be closer to the 10. So in the field, we have a combination of both. And that's where the data falls. So no surprise there. Nitrate. This was a surprise, sort of. Nitrate removal, it removed 20% of the year 1 plus year 2 loading. 11% of the cumulative 4-year loading. It removed 27 kilograms of nitrate nitrogen over 4 years. I've seen that. We saw this in our activated alumina filter in Ohio, where we had stacked a bioreactor with a activated alumina peer removal structure. And the activated alumina got coated with iron oxide, and it started to remove nitrate, which was shocking for us. And we determined from that it was not traditional. It shouldn't, right? Activated alumina and also these iron oxides, they really don't have any ability to absorb nitrate. And so we confirmed this in the lab. And so why? How is it removing it? Well, it's not like a traditional bioreactor where you have carbon as your electron donator. In this case, I call it abiotic. There is some slight biotic aspect to it, but generally what we have here is you've got iron 0 and iron 2 plus from the steel shavings that are serving as electron sources, the electron donator to nitrate. So instead of carbon, we have iron 2 plus. As that gets oxidized in a redox coupled reaction, iron 0 to iron 2 plus and iron 2 plus to iron 3 plus, serving as a sacrificial electron donator, where we have good water PSM contact. So the removal of nitrate was comparable to a wood chip bioreactor, but only a fraction of the contact time and a fraction of the size too at that. So this was a surprise. Hydraulic performance, there was no clogging or reduction in flow rate over the 4 years. It handled 8 liters per second, around a little over 120 gallons per minute. So we met our flow rate goal. There was no bypass, 0 bypass. That was one of our goals. There was no release of phosphorus when we had no flow, stagnant conditions. There's no indication of anaerobic conditions And the PSMs also remained unconsolidated with no concretion. We found in some tank filters in the past with the steel turnings mixed with gravel, in a top down where there's fluctuating wet and dry cycles, sometimes it'll get very hard like concrete, which doesn't affect the flow rate. It flows the same rate, but you can get preferential flow channels through that. We did not have that problem with this, because if you keep it moist, we found as long as you keep it moist, whether it's a top down or a bottom up, if you keep it moist, it doesn't harden up, it doesn't concrete. And in this case, it was still perfectly unconsolidated. I could just reach my hand in and grab it. So that was another advantage. As far as safety, we tested the treated water with a bioassay with the organisms. We sent it off to a lab in Indy to do that. 0% mortality. It was identical to ditch water. The pH of the treated water was near neutral, and no trace metals. In fact, what we found was that these filter media in this structure was reducing trace metal concentrations by adsorption to iron oxides, which is not a surprise, because the mechanism for phosphorus adsorption to those minerals is very similar to how trace metals adsorb to iron oxides and hydroxides. So this media can also, if you had, I mean, God help you, if you did have a problem with excess trace metal losses from your site, this could filter it. But this was a nice demonstration. But if you really want to use steel shavings mixed with gravel in a non-research real application, and you want to achieve both high flow rates and the long contact time, like that 10-minute contact time I was showing you in those curves, then you have to make it much bigger. You wouldn't put it in a tank. You would put those iron shavings in a buried bed. And here's an example of that. This is one we built in Michigan 5 years ago. This is on a swine farm. This is 40 tons of shavings. This is the bottom. This was a top-down flow. This is the bottom layer of drainage pipe. There's filling it with the gravel steel shavings mixture with the inflow pipe, and then we covered it with a tarp, buried it. There it is afterwards. This was designed to treat a 30-acre field and remove 40% of the cumulative 5-year load. It's a big load, and perform at a 10-minute contact time and a flow rate of 250 gallons per minute. This one, unfortunately, we didn't have automated monitoring on this one. Recently, I've been going up there the past couple of months taking grab samples. So after 5 years on those grab samples, it's still removing over 50%. That's how you would do it in practice with metal shavings, not necessarily a tank. The tanks are more reserved for smaller, more potent filter media, which is what we're going to put in this structure now that we're about to clean it up, which I'm going to show you the next slide. So to conclude, the bottom-up flow regime with constant water saturation using the steel shavings, gravel, it was acceptable. There was no release of phosphorus anaerobic conditions. There was no clogging. There's no concretion of the PSMs. The material remained unconsolidated, and we got appreciable nitrate removal. So a month ago, we cleaned out the tank. We used basically used like a septic vac truck and just sucked the 9 tons out. And then we replaced it last week with a activated alumina filter media, which is more expensive per unit mass, but much more potent on a per unit mass basis. This is 8 by 14 mesh. It's fairly coarse. It's granular. It's not those large pellets though. It's still granular. It'll have a higher flow rate than the previous activated aluminum we've tested in other filters in Ohio, which was a 14 by 28 mesh. But as a trade-off, it's going to require longer contact time. Again, we use the P-Trap software to dial in those details. So we'll begin monitoring this. Also, in your neck of the woods, I thought I'd mention this, South Fork Watershed. There's construction going to take place probably after harvest this fall. 2 peer removal structures in manure impacted sites that are going to have high P. They're both 8-inch tiles. This is with the ARS unit in Ames. Specifically with Dr. Ken Waka. He's going to construct these and monitor them. He's going to be using the smaller size activated alumina. We've tested that also in Ohio. It works very well. 14 by 28 mesh, bottom up flow. This site has generally peak flow rates of around 180 gallons per minute. So that to look forward to. Last thing, we do have a mobile pea removal demo unit that we could take around and to demonstrate different media and demonstrate how it works, teach people about what they are. But there's also training modules available, many hours of training modules to get trained on how to design and construct these. Also, just about how they work, more detail than you'd ever need. Also, a little bit on how to use the software. Yeah, if you just Google P-trap phosphorus, you can find all the stuff pretty easily. You can also get credits if you do it through the ASA. P-trap software is also available at the P-trap website. Again, it's freely available, and you can use this to design structures for your sites or to evaluate hypothetical structures. So, ready to take any questions, but first, getting ready for some of these future seminars.
So thanks so much, Chad. We got some great questions in already, so we'll get to those here quick, but some logistical items. I really want to thank our key partners whose funding make this webinar series possible: the Iowa Department of Agriculture and Land Stewardship, the Iowa Department of Natural Resources, the Iowa Nutrient Research Center, and the Leopold Center for Sustainable Agriculture. Go to the next slide. If you watch this webinar live and want to earn a CCA CEU, please email Elena Whitaker, ALENAW, at iastate.edu by 5 o'clock today, including your name, the name you entered to watch the webinar, and your CCA number. Again, ALENAW, iastate.edu. Yep, we can go to the next one, which is if you watch this webinar live and are willing to fill out a voluntary survey, we'd greatly appreciate it. Only one survey response is needed for all 2026 webinars. So if you've done that, thanks. And if you're willing, you can go to that website there, iowalearningfarms.org/survey, or scan the QR code. Next slide. Okay, we have a talk on harnessing local woodland resources to enhance bioreactor microbiome for water quality improvement. So we're going to go to the wood chip bioreactor and learn about the microbiome. So please tune in next week for that same time, noon, Wednesday, July 8th. And next slide should be, you can find this webinar and all previous webinars in the ILF webinar archives, either on our website or we have a YouTube channel just for the Iowa Learning Farms webinar. So if you want to, somebody that might benefit from Chad's webinar, please let them know that it will be archived there and go watch some of the previous ones. So a few questions here. What's the lifespan of kind of the non-tank type filter?
Yeah, good question. So it's whatever you design it for, right? And my philosophy for design is I try to design them to be as big as possible for the longest lifetime that is both feasible and economical, right? So what's that translate to for, every site's different, but if I try to think of the most typical sites of the Midwest, which this one is pretty dang typical, something between like 20 to 30, 20 to 40 acres, somewhere between like 3 and 6 million gallons per year. High P site, so pumping out around flow weighted mean concentration 0.2 milligrams per liter dissolved P. If we're talking about again, there's different ways to do it, but for metal turnings structure, we're talking between 20 and 40 tons of media, not in a tank. And I want to design that for that. That's going to get you around 10 years 40% removal over 10 years at least. At
Okay.
least. But this is the reason why you play around in the P-Trap software. You can look at all those different scenarios yourself and just in a matter of seconds, just changing those sorts of things in your removal goals. But if you want to, I mean, the bottom line is, if you want to remove more or have a longer lifetime, you build it bigger, and then it costs more. I mean, some of these we've designed for with 40-ton filters that could last 20 years, 40% removal. Now in the beginning, the removal is going to be more like 80%, 90%,
Yeah.
right? And it goes down. So when I say cumulative removal, I mean over that entire 10 years or 20 years, whatever your lifetime goal is, it means over that entire time period, you want to remove 40% of everything that goes into it. I choose 40 as my cumulative goal usually because that's kind of the sweet spot for most of this media. And it also happens to coincide with the Great Lakes goal of of reducing phosphorus loads to the Western Lake Erie Basin by whatever year
Okay.
they've chosen.
Where have you been able to source your materials for this?
For the steel shavings, in my neck of the woods, I've get it from generally you get it from big industrial recyclers. So for us, we got it from OmniSource, and they've got locations in several places in the Midwest. Sometimes we get them directly from the manufacturer. For some of the ones in Ohio, we got them directly from like the GM plant. In Wisconsin, again, there's different just industrial metal recyclers, and they're turnings. These are turnings mostly from like a lathe. They're drilling out blocks or whatever, and they're super thin. They're not all the same. You want to get the stuff that's nice and thin, no chrome, no stainless steel, just regular carbon steel. And so we've been getting it for around $300 a ton.
Okay. This might be, I'm thinking it's exciting to know a couple of these maybe go in Iowa. I don't know if Ken Waka would be willing to do some, maybe a virtual field day associated with this to kind of see what that material looks like and so forth when those get installed up at the South Fork. That's exciting. So,
Yeah, I'm guessing he would probably be interested in doing that.
okay.
And,
Okay.
they're in tanks, and one of the reasons why they're in tanks, so those filters may not necessarily be constructed to handle, 100%.
Yeah.
It's more for a demonstration.
Yep.
But because of that, they're in tanks. You take people out there, pull the lid off, and they can actually
Yep.
physically see it.
Great. What's the cost of the activated aluminum compared to the metal shavings?
So the activated alumina. So I give a really good comparison right now because we're going from one to the other at that exact site. And the activated alumina, I'm trying to think of the price they sold it to us for in bulk. We got it in super sacks. We put in 2.3 tons of it. Again, much less than those metal shavings, right? But the cost was, I think it was like $1. I think it was between $1.50 and $1.75 a pound. All
Okay.
right. So, actually, I'm going to pull up the P-Trap design for that site right now and tell you exactly. The thing is, though, okay, it costs more, but we're going to be able to remove. We're going to be able to remove a lot more phosphorus. It'll last a lot longer. Let me see here. Give me 1 second.
As you're doing that, there was a question that what do you do with the materials to dispose of? How do you dispose of the materials after they've reached exceeded their lifespan?
So it depends on the material. So the metal shavings, generally, you have something like there's often not much recognizable metal in it, and if there is, it's very small and it's very brittle. So what we've done in the past, a lot of times farmers, they like, it's mostly gravel. They like gravel, and you'd use it. They use it filling potholes and that on lanes, but the phosphorus is bound in it tight, so there's not much of a concern of it being re-released. Still, it's like move it someplace where where it's not not a high P area. It's just it's other media like the activated alumina, some other things. They can potentially be regenerated and reused again.
Okay.
But at the end of the day, a lot of those they can just be land applied.
Okay.
They don't think that you're going to get a benefit of reusing it as a fertilizer because there's not enough phosphorus. It's not concentrated enough on it, and it holds on to it so tightly. I wish I could tell you that, but it generally doesn't. Unless you're treating something like wastewater and really saturating with a high concentration of phosphorus for a long time, you're not going to be able to get any re-release of it for fertilizer. And at the end of the day, if you think about it, you look at the numbers of how much is bound onto it, it's really not very much. It's large, massive phosphorus you're removing relative to water quality, but you remove 20 pounds of phosphorus from a field, that's great for water quality, but 20 pounds of phosphorus over 20, 30 acre field, that's nothing for agronomic needs. I mean, you need 40 pounds of phosphorus per acre per year for corn. Yeah. So, taking 20 pounds and have it spread out from 1 year, spread out over 24 acre, it's nothing. So other materials, you can get other benefits. There's different materials, drinking water treatment residuals, sometimes slag, which I don't recommend slag for tile drainage, only surface water. Flue gas gypsum, you can land apply those and get other benefits out of that. Real quick, here's the comparison at this filter, at this site for what we get out of the activated alumina. So again, the cost, we have 2.3 tons, somewhere between $1.50, $1.75 per pound. But we're going to, if you look at the removal on this scenario, year one, 41% removal, but it's going to hover around for a lot longer. After 5 years, you'll still have cumulative removal of 32, almost 33%. So, it's a different way of going about it. Again, it just depends on the site and how much space you have, what kind of flow rates you need to handle, what your P loads are, the concentration. So it's not a one size fits all, and that's why we created the software. Does that answer the question about cost?
I think so. And so there are a couple questions here about the dissolved phosphorus that you see. Do you see a spike in dissolved phosphorus in the tile drainage after surface applications of P?
Oh, yes.
Okay.
Absolutely. Yes. We see spikes not only after application of phosphorus, but also even that set aside. So at this site, by the way, they're not adding phosphorus anymore because the soil's already built up. But in we do a lot of monitoring, many other sites, but we do observe that. In fact, a lot of times the largest portion of the annual load is coming from what was recently applied. But that set aside, even when it's not applied, we see the spikes occurring with peak flow rate. So usually just, your 3 or 4 biggest flow events of the year. And it's not just because of discharge volume, the concentrations will spike often with those peak flow rates because there's much, you don't have as much contact time between the water and the subsoil. Consequently, Mark Williams and I, our hydrologists, are working on a tool to be able to identify hot spots in the Midwest that are going to produce the highest concentrations of dissolved P in tile drainage. It's like a phosphorus index exclusively for tile drainage. And something like that could be used then to identify where's the best locations to put a P-rule structure. We kind of did that a little bit with the ACPLF software. I worked with Sarah Porter and David James on that, and that's in there now, but it's kind of, shooting from the hip,
Yeah.
We're going to make something. Yes.
What are some of the factors that that would play into that? I'm just thinking kind of from an Iowa perspective here.
Depth to the tile, spacing of the tile, proximity to CAFOs, the prevalence of surface depressions in the field, the presence or absence of Hickenbottom risers, and then there's various soil properties that go into that consider the ability of the soil to filter the water as it moves through the topsoil on down into eventually into the subsoil in the tile drain. There's other factors as well. That just comes up
Yeah.
first thing in my mind.
Okay. Have you tried this type of filter in drainage ditches?
Yes. In fact, some of the first ones we constructed were in ditches around 2008, 2009 on the eastern shore of Maryland, on the Delmarva Peninsula. There's extensive network of ditches. They don't have as much tile drainage, but it's surface water that they're taking out with the ditches. And these were primary ditches, right? So these were on-farm ditches. So they're small. They're like the bottom, the ditches are the bottom probably like 5 feet wide on the bottom. They're trapezoidal, and on the top they're probably, I don't know, maybe 20 feet wide at the top. So they're not huge ditches, but we were building filters. That time we were using dominantly flue gas gypsum because it was free, highly available, and steel slag, which again works fine for surface water. Don't ever use steel slag for tile drainage water unless you want to change the filter out annually, which is fine. If you want to change out annually, that's fine. But anyway, we use those two media in the ditches, directly in the ditch. Like we had a network of pipe. I might even have a picture of it. Actually, I can show you on that in one of those slides. A buried pipe in the. There you go. This one right here. This shows a ditch filter that is filled with water. So I know it's small. Little inset right here. This is before backfilling it with the media. So this is in a ditch right before a culvert. We put a flow control structure at the culvert. Here's your drainage pipe buried before it gets buried. Backfill that with a filter media. And then, so basically the culvert acts like a small dam, and the water drains through that media down into that pipe and takes across the road or wherever it goes. So we built a bunch of those. There's other ways to do ditch filters. If anybody ever wants to do a big ditch filter, I have some designs that I would love to try out, because something like this only works on your small on-farm primary ditches. If you want to try something bigger, I've sketched some things out and done some designs in P-trap. I've just never built them. But if somebody has the resources to do that and wants to give it a shot, I can. I've got some options for you.
Okay. Are these practices being used in Illinois that you know of? Anybody doing any work in Illinois?
That is one state I've only given one presentation on this in Illinois in the 10 years that I've been in the Midwest. Ohio gets lots of activity. So I think I had contact once with like a homeowners association that wanted to treat their water before it accumulated and went to one of their local ponds. But there was some research there that they had a research filter. It was really tiny. It only had like maybe 100 pounds of media in it. It was something real small, and it really was under designed and really couldn't handle the flow or the P load for a site. It was a research site at University of Illinois, but really, So no, not really. They have not, but I sure would like to.
Okay, so that person maybe can reach out if they have some interest. So maybe one or two more questions to be cognizant of your time, Chad. Is the nitrate removal results are interesting. Would you expect the continued rates of that N removal into subsequent years?
I do expect that. And the reason why is because it's, that mechanism is totally different from the phosphorus removal mechanism. Whereas with the phosphorus, the iron is becoming more and more saturated. It's a surface adsorption reaction. The iron gets more saturated with phosphorus, and as it gets more saturated, its ability to remove further phosphorus decreases. But with that nitrate reduction, as long as that iron is still present, it's not becoming saturated with nitrate. As long as it's still present and is still able to basically become oxidized, as long as you still have steel physically present there, then it's still going to keep doing it.
But am I correct? The aluminum one wouldn't remove nitrate?
So that one
Okay.
we did, and I don't know if it's an
Okay.
anomaly or not. And this
Okay.
one's published. If you want to look at it, it's in ASABE. It's called. Mark Williams came up with a great title for it. It's called "Stack 'Em Up,"
Okay.
where we stacked. It was a P-removal structure with a bioreactor,
Okay.
and I don't know if that's an anomaly or not.
Okay.
But the activated alumina, you saw the picture of it. It's white as snow initially.
Yeah, right.
And it didn't take very long. That was a bottom-up flow. It was a bottom-up flow through it, and it turned red, right? So, tile
Okay.
drainage water often is going to be high in iron 2 plus,
Yes.
right? Because
Yeah.
the high water table. And so as it basically it oxidized and through that process hydrolyzed on the surface of the activated alumina.
Uh-huh.
So the activated alumina we think just served as basically a seed for the hydrolysis of that iron, so it could precipitate, and then again for the oxidation of that iron going from 2 plus to 3 plus, and then 3 plus then hydrolyzing. So we don't know if that's an anomaly or not. It did it there.
Yep.
I don't know. All I know is for a fact, activated alumina on its own will not absorb nitrate.
Yeah. Yeah.
It
Okay.
shouldn't. It doesn't have the right functional
Yeah.
groups.
Well, Chad, thank you very much for the excellent presentation. Excellent as always. Thanks for being willing to do another Iowa Learning Farms webinar. And thank you all for the great questions. Sorry we couldn't get to all of them, but I want to be cognizant of the time. Again, email Elena Whitaker, ALENAW at iastate.edu if you want a CCA CEU. With that, thanks very much, and please tune in next week.
Thank you all. Take care.